4 minutes. All right, everybody. Welcome, everybody. Good afternoon. Really appreciate this opportunity to introduce my role model, Professor Steve Leone. Professor Steve Leone received a PhD from University of California, Berkeley. After a short stay in another USC, University of South California, as an assistant professor, he moved with two hats. One is a faculty member of University of Colorado, another is a staff scientist at the JLA, standing for Joint Institute for Laboratory Astrophysics. And so overwhelmingly, in that period, he had lots of accomplishments. Later on, I will mention some of them. In 2002, he was joining back to the University of California, Berkeley. And by then, he started from there. He wears three hats. One is a professor at chemistry, and second one is a professor in physics. The third one is a researcher scientist at Lawrence Berkeley Laboratory. So he has been extremely successful in many aspects. And for any of you who are interested, I would not have time to cover everything. He has collected double digits awards, recognitions, honors, not only in the United States, but also in Europe and also in Asia. And just in the United States, he also collected double digits of awards and honors from both American Chemical Society and the American Physical Society. So back to even 1995, he was inducted to National Academy of Science. And also then he was recognized being a fellow of American Academy of Arts and Science. So today, since we had already a few minutes cut off from the awards ceremony, I want our youngsters, particularly those of you who are in my condensed matter physics class this semester, be aware of a few keywords here. One is the attosecond. So this is one quick quiz. Anyone is willing to answer me what is the attosecond is about? What is the duration? And the second one is something called coherence. And make sure these are two keywords for today's lecture. So without further ado, I would like to welcome Steve for his lecture.
Thank you very much, Rongying, and thank you for a wonderful day that I had here today. I always measure by how many new ideas I'm getting when I talk to people, and it was really terrific for me. And thank you for the invitation. I wanted to tell you about work that emerged in our lab in solid state physics by dreaming that we could do things at very short time scales with attosecond pulses. And attosecond pulses you need to make them in the extreme ultraviolet or the X-ray. I'll tell you a little bit about that. And it involves a kind of very different spectroscopy. So I want to show you how that works. And then today, I'll also talk a lot about coherent processes that happen. And I'll need to give that a little bit of a turn as well. And these are some of the agencies that have funded our work. These are some of the agencies that have funded our work, and so on. So in 1887, Edward Murbridge did what I think is the first time-resolved pump probe experiment. It was done at Stanford. And this Murbridge actually has a very checkered history if you ever want to go read about it. And anyway, he was funded to put a bunch of tripwires on a racetrack, and the horse would gallop by and trip the wire, and a camera would flash, and then go to the next wire and the camera would flash. And the tripwires are like our pump pulse, our trigger, for time-resolved pump probe experiments, and the camera is like our detection, our probe pulse that we do in all of our time-resolved experiments. Now, he noticed, and here's the new science, that in one or two of the frames, all of the feet of the horse were off the ground at once, at a gallop. So this is quite amazing, and new science was learned about how this horse was really running. Walt Disney then, very quickly after, figured out that you needed a certain frame rate to fool your eye so you could think that you saw a continuous movie, basically. So all of these things are connected historically with our vision of, like, how do we make a time microscope and take movies of things? And we take movies of spectroscopy. So in our lab, instead of the tripwires, we have a big powerful laser, and we create a pump pulse that does the excitation. And then instead of the camera, we create an XUV attosecond probe pulse that takes a snapshot of a spectrum. And this is, so all of that tripwire gets condensed into hardware, a vacuum, and laser optics, and so on, which gets, quite complicated, but it allows us to study materials in new ways. Now, without some key new discovery, in time by chirping the pulse, by making it have a lot of colors, so the colors all arrive at different times. Then go through the power amplifiers, and then compress the pulse again in order to get the very short pulses. So without this, we have no powerful lasers to do these very short pump probe experiments. But these lasers are about, maybe they could be typically 10 or 20 or 30 femtosecond. They're not really attosecond. So there was a second important physics that came, and that was the process called high harmonic generation, where we take a strong pulse, this red pulse. This is the field cycling here, and here's the envelope of this pulse. It can be like maybe 5 femtoseconds or something. And we inject it into a rare gas, and the pulse is so strong that it distorts the Coulomb potential. So the normal Coulomb potential is bent over, and an electron can tunnel out and then gain a lot of energy from the field. Then the cycle of the laser phase reverses, sends the electron back. Then it can recollide with the atom and then produce a burst of X-rays or XUV light. So here are near the zero crossings are the bursts of XUV light that are coming out. And if we would make the pulse shorter and shorter, you get almost for free an isolated attosecond pulse. So when you achieve isolated attosecond pulses, it's like making a white light continuum up at around, say, 60 or 100 electron volts. Did you have a question? Or?
Yeah, I have a question. So it's the high intensity laser field, capital EL, that ionizes the rare gas?
Yeah, almost ionizes. It tunnels out and then reverses.
And the electron in the rare gas comes back to
and collides.
Collides.
Collides,
Okay.
yeah. Recollides and recombines. A small.
And emits a photon.
And emits a photon, yeah. And this process, called high harmonic generation, is how we make our probe, in most cases, for the absorption that we're going to look at. And now, if you think about materials, so here's a whole lot of different pulses that we can make, and here are just some of the elements that you could probe, say at the M edges, the lower inner shell core level transitions that we can now probe, like zinc or copper aluminum or selenium or so on, and I'll be showing a little bit more about this in a few moments. So now, how did this come about? Well, the Nobel Prize was given for physics in 2023 to Pierre Agostini, Ferenc Krauss, and Anne LaHoulier, and I had the great privilege to go to the Nobel Symposium that occurred prior to the award of this, where the Nobel Committee was researching whether this was a good field to give a prize. And Pierre Agostini had figured out how to make a train of attosecond pulses, and Ferenc Krauss had figured out how to make an isolated attosecond pulse, and Anne LaHoulier had been the really key person to understand the process of high harmonic generation, and that's why they awarded it to these three. And there they are in real life. And I've had just beautiful collaborations with Ferenc Krauss and with Anne LaHoulier, and it's been a very close and professional interaction that to me has enriched my science a lot. Now, I actually don't want to just make pulses, which is what the prize was for. I want to actually use it to probe something, to see some dynamic process. So before we probe something, let's ask if we have X-rays or we have XUV, what do we see? Well, you know, Wilhelm Röntgen discovered X-rays in his lab. It was right beside his house, and he had a little Crookes tube. He was bombarding a metal with a high voltage electrons, and he saw this radiation was coming out on a fluorescent screen, and he accidentally started putting some things in the path, and they were still hitting the screen and illuminating, and he realized he had something really new, and he even waved his hand and realized that there was something really special going on. He brought his wife, Anna Bertha Ludwig, to the lab and put her hand in, and she exclaimed, "I have seen my death." And now what is this? This is X-rays penetrating bone density and showing some difference, right? This is not yet spectral, but it's really important. And in a really brief, like a week, he had made this so much better. He brought his friend Albert von Kolliker, and this is the picture that he obtained of this person's hand. And I think you would agree, like if you had this in like 1895, this was like really a new way to do medicine and all these things, and it's been important in so many areas. Now, if I went to a synchrotron, I would see a lot of people obtaining data that looks something like this. It's a whole lot of spots on a big detector. And what this is actual X-ray diffraction. If we take ordered crystals of something, then the ordered arrays will diffract like a grating and give us all these spots. And we could unravel all these spots by taking an inverse, essentially, Fourier transform, and understanding something about the phase factors, which is the difficult part of the problem, and we can get all the distances between atoms. And so we can actually plot where all the atoms would be in some complicated crystal or something, and that's great, but that's also not spectroscopy. So today we want to talk about spectroscopy. So what does X-ray or XUV transient absorption, how is that based? Well, if I had a molecule AB or a solid with AB, I would excite from an inner shell, which I'll call a core level, and I'll go to wherever there's a vacancy in a valence shell. So I would get a spectrum through the eyes of the A atom and a different spectrum through the eyes of the B atom. So if the B atom, say, had electron withdrawing, I could see that. If I made an excitation and changed whether an atom was neutral or more ionic, I would see this and so on. And this spectra, this type of spectroscopy is ubiquitous at like all synchrotrons and free electron lasers, and people really understand a lot about how to do it. And it's it's element specific, it's oxidation state specific, it's even spin selective. You can do chirality, we can do X-ray magnetic circular dichroism and so on with this type of spectroscopy. and it's very state selective. So, and there's a nice little review we made on this to tell about all the benefits of this type of spectra for ultra-fast processes. So now, in the solid, rather than having, discrete levels, like I was showing, we have bands. And so this is just germanium, for example, and you have a valence band, I have a conduction band, and I could excite across the band gap from the valence band to the conduction band. I could take electrons from the valence band and put them in the conduction band. And now if I were probing with this transition from the core level of germanium, I would see that the absorption would be reduced in the conduction band. And then I would create holes in the valence band, and I would see when immediately after I make that excitation, that there's new absorption to the valence band. So I expect one should increase and one should decrease, and I would see this immediately around the band gap. And we call this the state blocking and the state opening. Some people would say state filling or something. It's a basic mechanism that would help us understand how carriers are changing between valence and conduction bands and so on. So this is a kind of important principle. And we could do it, here's our little pump probe set up, and we could do it in absorption like this, or we could do it in reflectivity, or we could make gratings. We could write gratings with two light beams that interfere. So there's a lot of different kinds of ways we could do this simple experiment where we excite across a band gap. And the only problem with the absorption is the samples have to be really, really thin because the M edges are so strongly absorbing. So it's kind of an inconvenient place to work, but we do pretty good on it. And if you're interested in the reflectivity, it's this paper here by Chris Kaplan. So let's start with a really simple question. So if I had iron oxide, it's Fe2O3 hematite, and if I excited it with blue light, what would be the possible transition? Well, one possibility is that it would be called a ligand to metal charge transfer. That would be when the oxygen would donate an electron to the iron. And the other could be, it would be an iron like D to D transition. So these two are very distinctly different. If the oxygen transfers an electron, then the iron changes from iron 3 plus to iron 2 plus. But if it's a D to D transition, the iron is still in its same charge state. So we would be able to distinguish these if we could see the charge state of the ion. So we could do that experiment. And first of all, look here. This is the Fe2O3, the normal absorption in the XUV. And it's around, say, 60 electron volts. And we know in Fe2O3, if you make it correctly, it's all iron 3 plus. And this is the neutral metal. So you could see that there's a big difference between the 3 plus and the neutral metal. And in addition, there's a big difference between 3 plus and 2 plus. So if I perform this experiment and I look at one of these peaks decreases and one of these peaks increases here, we see the iron 3 plus is disappearing and the iron 2 plus is increasing. So we already have a new piece of information that when we excite this material, it's a charge transfer from the ligand to the metal. Yeah.
Are you varying the energy of the incident XUV?
Yes, this is the energy of it's this broad band. So we're taking the entire broadband continuum and then spectrally resolving it afterwards.
I see.
With
So you're
grating.
saying which got absorbed more?
Right.
Okay.
Yeah.
And what is M delta A? What's that unit?
This is milli delta absorption.
Okay.
Like it's delta. It would be delta OD.
Delta minus 3.
Milli delta OD.
Okay.
Optical density changes. Yeah. And now, however, if you stare at this data for a little while, you realize there's something more, like if everything were just 3 plus goes away and 2 plus appears, they should kind of all like reach a point here, but instead there's a shift going on. And this shift was convexing, like a very confusing for a while, and a lot of people in the group were working on it. And what we realized at one point is that it's probably due to what's called a small polaron formation. That's where you trap an electron by a phonon, by a vibrational mode in the solid. And so Scott Cushing, who's now on the faculty at Caltech, worked out what would be the spectrum of the ground state, what would be the spectrum immediately after excitation, and what would be the spectrum if a polaron forms. And he showed very exactly that this was the process that was happening, and even the amount of the polaron, what fraction was polaron, and so on. And so why this is significant is, in addition to detecting that we saw the charge transfer, we're also saying we can detect quasi-particles. So not always. You know, we hunt all the time in our lab for any signatures of quasi-particles, but this is one that's very evident, that we see the formation of this polaron where the electron charge around the iron is strongly influenced by the vibration, basically, by the change in structure due to the vibration.
And this polaron lifetime is 2 picosecond?
Yeah, that's very long. These are, in this material, it turns out that the charge transfer and the polaron is long-lived.
Okay.
Not always, but not always in every case. But yeah, so now for me to proceed to kind of the next level of discussing what can happen, I need to bring in coherence. And so in quantum mechanics, interferences are kind of like the heart of quantum mechanics. So we deal with wave function amplitudes, we sum wave function amplitudes to make superpositions, we square those, and we get cross terms. If we get cross terms, then we get interferences. And so everybody knows the two-slit problem. We put light waves in, we don't know which slit it went through, we get spherical waves from diffraction of these apertures, and then we allow them to merge on a screen, and we see the nice interference pattern. So what is not as obvious is if we excite two states simultaneously and create a superposition and then detect them to the same final state, we also get interferences. So
and these two states have to be same energy?
No, they're different. They're completely different energies.
Okay.
Yep. So the mathematics of that, in just a 2-second view, is we sum two wave functions like this, an amplitude, a wave function, and a frequency factor, the e to the I minus I omega 1 t with the other, and now we square it. And when we do the square and solve the algebra, we find there's a constant part, another constant part, and then a time varying part, an oscillatory part. And here is what we call a quantum beat, or an interference. So we're going to see in a number of cases where we create coherent phonons in solids, and this is the mathematics of how to think about it, where it comes from. So just think, we sum wave functions, we square them to get real things that we can look at. When we square them, we get cross terms. And here's that cross term that comes out eventually when we solve the algebra. So now let's think about 2D metal dichalcogenide. And 2D metal dichalcogenides could be like molybdenum sulfide, and you would like put it in your lock as a good lubricant, right? For years and years, it's black, you think it's worthless. But Tony Hines showed if you peel off one layer of this material, it becomes a direct gap semiconductor, which is rather special. So it goes from an indirect gap to a direct gap. This is shown for WS2. And this has a bright luminescence. It gives all kinds of new phenomena. We can peel these layers and we can stick them back together with twists. And so we have born this whole field from Tony Hines by just discovering that if you peeled off one layer, it has all these new properties. So this is kind of special. Yeah, and so we can take a material, it's called molybdenum telluride, and it's a semiconductor with a direct gap. So it's the 2H phase, which is a semiconducting phase, and we can take about 10 layers. We don't have enough signal to do one layer, but we have enough for about 10 layers. We get about a 50 nanometer thick, and we can excite across the band gap in molybdenum telluride, and then we can probe the XUV absorption through the eyes of the molybdenum and the tellurium now. So not just one material, but two. And let's look what happens. So if I see the molybdenum, it comes at around 35 electron volts, and time is going up here. And initially, it's very broad. And if you follow it, it gets narrow. And so this is the holes in the molybdenum, showing through the molybdenum in the valence band, and they're born hot, which is why it's so broad, and then they narrow up as it's cooling. And we see the same effect in the tellurium, that it's born hot here, and it's cooling. But then if we look a little more carefully, so this is in the valence band, and now if we move over a little bit, it's in the conduction band, and we're following electrons in the conduction band. And we see right away, like our eyes, we don't need AI to do this. Our eyes just tell us, whoa, something new. It's like flashing on and off like a beacon, like being like a lighthouse or something. And there is some coherent phonon motion happening in this solid. So this is our first kind of really big example that we just like stood out, like, oh, you easily make coherent phonons in this material, and you can also tease out information about the hot electrons. I won't go into detail today. But let's just take one example. Like, suppose I want to follow the hot holes, and I want to figure out what is the time scale. Well, it turns out if I pick a region and measure carefully, I can see this shift here of the center energy of this hot hole distribution. And there's a very fast part. It's 15 plus or minus 5 femtosecond. And there's a slower part, which is around 380 plus or minus 90 femtosecond. And we can assign this to the fast part to the carrier-carrier scattering. So it's like a rapid thermalization. So it goes from a non-Fermi-Dirac distribution to a Fermi-Dirac distribution in like 15 femtoseconds in this material. And then we see a slower, and this is when the hot carriers are interacting with the phonons, and that's the decay of the hot carriers due to interacting with the lattice. The lattice band, the lattice interaction due to the phonons. Okay, so a lot of different materials have been studied, and some we've studied ones that have like 1 or 2 femtoseconds, some that have 30, 40 femtosecond. They all have different carrier-carrier scattering, and I'll talk a little bit more about that tomorrow. So let's just see in pictures. I like to go a little bit mathematics, a little bit pictures, a little bit intuitive. I hope you don't mind. And so what we do is with the laser pulse, we create hot holes and hot electrons. And initially, they're not Fermi-Dirac. So the first thing that has to happen is they have to thermalize to become more like a Fermi-Dirac distribution. They should obey Boltzmann statistics, essentially, and they will on a very short time scale. And then, eventually, that should communicate with the lattice and cool down, and eventually we should get back to room temperature. Okay? So this is pictorially what's happening here, and we're probing it through, say, the 4D core level of the tellurium. So now what about the lattice? So initially, let's say we have a perfect lattice. But then we excite across a band gap, and that changes the potentials. So maybe the potentials will have a smaller gap, and they may be distorted in some way. And the lattice will now have to respond to that change, that the potential abruptly changed. And there could be two mechanisms that Millie Dresselhaus has told about this in lots of papers initially, like there can be a displacive electronic excitation, which is just this dramatic change in the bands, like this. It should apply mostly to the symmetric modes, in the phonon modes in the lattice. Or there can be an impulsive stimulated Raman, where you pump up and pump back down again with a short pulse, and that can involve asymmetric modes. So these have been described, and they happen. One of them happens almost instantly. Well, both of them kind of happen instantly, and then in addition, the hot carriers can kind of feed this to do more. So here is a blow up of these coherent phonons here. You can see it's bright, it's weak, it's bright, it's weak. And we can get the phonon periods out and see which modes are playing a role, and they're coherent in this case. So that if not, we would not see this. We would not see this modulation. So if we take a line out of this data, we can fit it or do a Fourier transform and find there are two frequencies, one around 5 terahertz, one around 3.7 terahertz that are underlying this coherent phonon motion. Okay, and now we can, here's the Fourier transform, and we can assign through the known Raman spectra, the one higher frequency is the A1G mode, and the lower frequency is the E1G mode. And here they are, from the data, just doing the Fourier transform. So now, normally the weak E1G mode, it's a non-symmetric mode, and it's usually not observed very well. But the point in this experiment is we're very sensitive to the core level potentials. I should wave it this way. So as I stretch or compress a bond, I'm riding on a very steeply repulsive core level potential. So it turns out we are very sensitive to these modes that can be produced, whether they're produced by impulsive Raman or by the displacive electronic excitation. And what's really neat is the A1G is across the planes of the material, and the E1G is within the plane of the material. So we're actually resolving these two very different motions in the lattice in this case. And we think, of course, one looks like the displacive electronic, and one looks like the impulsive Raman. So that's a hypothesis of the outcome of this. So now,
Steve, so in both of these, there is no nuclear displacement, only the electrons displaced.
the initial excitation is electronic, and the Raman would also put you in a new place on a potential surface.
But the lattice side will not change in that fast, right?
Not in that fast.
Okay.
Yeah. Correct. Yeah. Okay. Yeah. So now, if you think about phonons and like phonon carrier, like interaction of carriers with phonons, what you realize is that you often try to devise like multiple temperature models to describe things. Like you might say, there's an electron temperature, there's a phonon excursion, that's maybe you could relate to a temperature or something. And so Ramon in our group, when he was here, when he was in Berkeley, he wanted to pursue the phase of the phonon excursions and project it onto the phase of the electron and hole temperatures. So assume the material has already reached the Fermi-Dirac distribution. And what you see is that when the phonon excursion is small, the amplitude, the temperature of the electrons and holes is high. And when the phonon excursion is large, is high, the temperature of the electrons and holes is low. So they're completely anti-correlated. And you might think, oh, now we've discovered like the hugest new thing, but it turns out if you turn back the clock, there was a theoretical paper already in Physical Review Letters in 2011 that exactly described this phenomenon should happen. And it's just a thermodynamic effect that you only have a certain amount of energy and you can partition it either between phonon excursion or electron hole temperature. So they're completely anti-correlated. And we did it at 2 different power densities and everything checked out, very precisely according to the description of this theoretical paper. And so it's important to note that, so we're now getting at the carrier lattice interaction in detail. So this is possible in these types of measurements. So now we got excited about coherent phonons, and we thought we should really, educate our students, our undergraduate students, to this type of experiment. It is much too difficult to bring an attosecond laser into an undergraduate laboratory, but by reflection, by pump probe reflection, you can easily measure the coherent phonons in a material like antimony. So now our undergraduate students perform this experiment. They learn about pump probe, they learn about correlation, and they learn about coherent phonon and the different mechanisms of coherent phonon. And Alana, who's now on the faculty at Reno, was the one who heroically made this work for a very small amount of money in our laboratory, and it now is part of the routine that we operate in that lab. So now let's press on just a little bit more. And there's a interesting material called SIGS. It's copper, indium, gallium selenide, and it's a quaternary kind of metal dichalcogenide. And it has a very high solar efficiency conversion to electricity, around 24%. Doesn't really beat silicon. I mean, we're still going to put silicon on our house, but for some applications, this has been very important. And to get this high efficiency, it turns out you have to grow it deficient in copper. So you have to purposely introduce defects due to restricting the copper in the growth. And I want to show you why. And so when you grow it with a deficiency of copper, the material segregates. So you have the normal SIGS stoichiometry here in the white, and you have the deficient copper region segregating into these planes. So they're like buried heterostructures in the material. And these carry, I believe, these carry the charge carriers better out to the electrodes that you need. And that's why it improves the efficiency. So the copper deficiency allows a better carrier transport that allows this material to achieve its very high efficiency. And these are just about 3 nanometers, so it's really small planar defects that are appearing. But the important thing is there are 2 different materials underlying this when we try to understand the dynamics. So if we look at the phonon and the carrier dynamics, which we've done, we see immediately that there's coherent phonons happening. So time again goes up. And whenever you see this blinking, you know that there's something new happening with the coherent phonon on the right time scale. And we can get the line outs of these and so on. And what you find is that when you analyze the coherent phonon, you get two different frequencies, one for the normal SIGs and one for where the copper is deficient. They call it the ordered vacancy compound. This is the copper deficiency. So you get 5.26 terahertz and 4.77 terahertz. And this is like real, to me, you know, like when a person in the group brings a data like this, say, okay, wow, I'm really seeing there are these planes. This is not just joking. You know, that people say there are these planes. The planes are really there. Because you see it in the coherent phonon motion in the real sample that you're studying.
Is there a simple reason why the frequency is smaller in the copper deficient region?
Just a different, you know, I don't know the exact order, you know, like exactly the mode and
Okay.
which one, why it expands,
Okay.
you know, but it does expand.
Okay.
Okay. Right. Okay. So now, because we know this has two different materials in it, we can look for other things, and we had a hint, like a glimmer of this, and then we tried to do a better measurement. If you go back to just one of these blobs of the coherent phonon and look at a shorter, much shorter time scale now, so you have to take points that very closely spaced, you find there's another oscillation. It's about an 18 femtosecond period, and it turns out that period exactly matches the difference between the band gap energies of the SIGs and the OBC. So you think, oh, now I'm observing an electronic interference between two band gaps that are slightly different. And this is new. So there are very few examples of electronic coherence in semiconductors. And we see it in this material that's submitted in the paper, Physical Review X, and then we're waiting to see what people will say about it. It was all very new work, but it looks like a true electronic coherence occurring within each blob of the vibrational phonon coherences. So now all of this was like transient absorption, and when you do transient absorption, you have one pulse does some excites and then one pulse probes, and you're still kind of doing like linear spectroscopy with the probe a little bit. You can't do anything nonlinear, exactly, is maybe the better way to say it. But there's other forms of spectroscopies like wave mixing and so on. And so, for example, you could do a 4-wave mixing experiment where you mix a attosecond XUV pulse with two 800 nanometer pulses from a phi-sapphire laser called near-IR, and you could get new emissions that are born due to the interaction of the near-IR pulses with the XUV. And those can be what we call wave vector matched. So we have to match not only the energy, but also the angles lead to the momentum matching. So when we get
And also the photons?
Photons, all photons. And so, for example, if we put in an XUV and have the two beams coming at different angles, we can go, say, from this region down and then back up and get an emission. And it comes out at a new angle. And what's exciting about this is called background free, because you're not blinded by the main XUV beam. You're coming at a new angle where there was no emission before. And here you can see, this was done was Krypton, or I forget, it probably was Krypton, that you can see that you can get higher orders. So you can have not only forward mixing, but 6-wave mixing and so on. And the camera image allows you to see all these different orders of wave mixing. So when you do this, like in a gas, like this was done in argon, you can get all these beautiful coherences among electronic states in the gas, and this entire image is a background-free, like, so there's no scattered light or other things in the path. You're seeing only the weak emissions from the forward mixing map. So taking this lesson from the atomic work we were doing, we decided to try it in solids. And you know, in some solids, you can have, for example, like in sodium chloride, you can have very isolated sodium atoms that have normal, like S and P, and they look atomic-like states. And they give rise to features in the spectrum that are very sharp and look atomic-like. So, for example, if you look at the sodium plus in sodium chloride around the L23 edge in the XUV, you see this beautiful, you know, peak, which is a sign to almost an atomic-like transition. And there are like Rydberg-like kinds of features and so on. And this type of feature is called a core excitonic state, or a core exciton. And it's been studied a lot to understand the mechanisms of the decay. They're very short-lived states. They could decay by a phonon mechanism or by an Auger, like where one electron falls down and another is released, and or by electron exciton correlations or exciton-exciton correlations. There could be a lot of different mechanisms in a solid that you don't have available in a gas. So we wanted to study this, and we started in sodium chloride, and you can look at either the initially excited state, or you can look at the states that are populated by one of the near-infrared photons. So, for example, this is a map in time of the emissions from the initially excited state. And this is a map in time of when we first excite and then we dump it back down to a neighboring state and then observe by a delay the emission. And you see they're quite different. And you also see that there are some very bright features, but then there are some weaker features that come in later in time that have new spectral components. So why could this be? Well, if you calculate some of the possible orbitals that can be involved in the sodium chlorides, around the sodium, the kind of Rydberg states that could be involved, some look like S states, like this. And so here's one that looks a lot like an S, like a spherical state. You see there's little blobs of yellow. But others look like P states. So here's one that looks like a P state that's kind of tilted. Here's one that looks like a P that's kind of vertical. And you see again, there's these tiny little, like the wave function, creeping out among all these different, kind of residing on multiple atoms. And so, for example, it could start in one set of orbitals, and by collision or by interaction with the solid, it could change from a P-like this way to a P-like that way, and it might have a slightly different energy, and the energy would go to the lattice. So we believe all of these features are real. And so we started going back to think about the linear spectrum, which is the black line, and fitting the linear spectrum, and then realizing if you collect all the data at the different time delays, instead of just being 3 big features, there's at least like 5 features underneath here. So you understand that there's a lot more underlying these features when you see these core excitons. And we've spent a lot of time thinking about the mechanisms of what plays a role in the decay, and we think the electron-phonon coupling, there's a specific mechanism that a phonon is launched when you create the core level exciton, is still the dominant way that these relax. And you see the relaxation is very, very fast, like sometimes a few femtoseconds. And so this has taught us a lot about core level excitons in solids that we never thought we could do and understand through the dynamics. And so while I'm working on four-way mixing, I could actually think about a different alternative experiment that involves 3 light pulses, and that's called transient grating. It's also a four-way mixing, but it's different. So in the sodium chloride, I use the XUV first, and then I time the near infrareds later in time. Here, what I'm doing is I'm going to write a grating first with the near infrared. The 2 near infrared pulses will write the interference grating in the material, and now I'll diffract the XUV off of the grating. So this is just another way of thinking about the same combination of 3 pulses. So I write the grating, it's a carrier grating. So I choose the right material, I can make electrons and holes. And the electrons and holes have a periodic modulation, and then I diffract off that. And there's, in this material, there's a real and imaginary part of the dielectric function. So if you want to go back to your thing about your optics and so on, there's always a real and imaginary term, and the imaginary term gives us the absorption. But the real term we often neglect. It's responsible for the transient reflectivity and so on. And I want to show today we can get a lot of new information also out of the real term. So Rafa built up a setup in our group to do this. Write the grating, diffract it. So here's the diffracted beams. Here's the normal transient absorption on axis. This is the energy of the XUV photon. Here's the transient grating, the diffracted signal. If you block one of the lasers, the diffraction goes away. So you know immediately, you just put a card in and the diffraction goes away, you know you've made the transient grating. And this was done in antimony, which has a really great coherent phonon oscillation. So now, if you look at the maps, like this is a transient absorption experiment here, and you see it's rather complicated. You have a lot of things to deal with. If you do the transient grating, it's so simplified. Like it's suddenly really clear that there's a coherent phonon motion here, and then we can pick that out. You can take this signal and do a lot of work with like singular value decomposition. So everybody's computing and doing all kinds of manipulations on this data to try to find out what is underlying this and pulling out different pieces and so on. Or you could do the transient grating and vastly simplify the result. This is the point that I want to make. So rather than doing the hard work, you can get something kind of rather more easily, perhaps, in what you're going to find out. So you can also, by combining the transient absorption together, the TA, the transient absorption, together with the transient grating, you can combine it in the right way to get, for example, just the pure change of the index of refraction, the real part of the index of refraction. So we can think about it that the data we get first includes amplitude and phase, but when we combine it in the right way, we can get just the phase component or the refractive index component, and each of these can contain different information. And the key point is that we can take these real and imaginary parts of the time-dependent complex index of refraction, and we can build around it a very simple interpretation of sigma. So I just want to show you one example. So Vincent Eggers came to our group were just a few months from Germany, and he grew germanium films. First, this is the kind of signal you would get from transient absorption. And if you look, you can stare at the signal for like a long time and realize you've got a lot of work to do to understand what's there. And the work that you have to do is that you have to use an iterative procedure to deconvolve multiple pieces, like the state blocking, the broadening, the redshift. You know, you want to pull out just the carrier dynamics and maybe a coherent phonon motion or something, but you have to get all these pieces in just the right way, and it takes a lot of effort. So instead, Vincent did the transient grating. So he did the transient absorption, and then did the transient grating, and look what happens. You see immediately it resolves into two bunches, and one is the holes and one is the electrons. So without any work, he immediately can go to regions. And so he, for example, he says, well, I'll pick a region where there's a hot hole. Here's a region where the holes are colder. Here's a colder electron. Here's a hot electron. And he can get all the time scales with just lineouts without having to do all the massive deconvolution. So this, to us, was very exciting because it vastly simplifies the job of how you might pull out information from more complicated systems. So now somebody is saying they want to learn about Attosecond, and so just for fun, this is before the really good image drawing, so, you know, AI was available. I just asked Google Gemini, can you provide an illustration of a molecular Attosecond lab, one that's realistic, one that's artistic, and one that looks like a 1950s sci-fi movie?
Is that you, Professor?
It would be me, but
Okay.
I didn't give it my picture. It's probably Paul Kirkham, I'm betting. If you look at the resemblance, it's very similar. Okay, probably figured out Kirkham was a leading person. And these look like either the stretched hollow fibers or the high pressure chambers you use for pulse compression. So it's actually not bad. I mean, this part it's probably still too artistic, but this is not bad, you know, for an AI program to figure that out at this stage. And then this is the more artsy one. And I thought, okay, that's really weird. This is starting to look a little mysterious.
I like the tweed jacket and pocket
Yeah,
square.
exactly. And then this is the
that's
one
right,
based on
Leone.
the 1950s. Yeah, it's you. The 1950s sci-fi movie, Molecular Mysteries Unveiled: A Thrilling Journey into the Heart of Matter, the Attosecond.
Oh, Heart of Matter.
Anyway, I was excited about this. The students in my class didn't appreciate it, I think, but yeah. And then, you know, I'm not able to go twiddle all these knobs anymore. Too many things to review and stuff like this. But this group of heroic people have been pushing and pushing on this work to come up with these nice results. And I hope it was a learning exercise and not just a blitzkrieg of information. Thank you very much.
Thank you so much for the wonderful work. Yeah. Sure. Foster's? Yes.
And I have a question about the coherent phonon. Is it material specific? If you have a material that has a lot of different phonon that is pretty close to
Yeah.
energy, will you still be able to see these things? Or
Yeah. So some materials like kind of really give strong signals, and some materials give weak or none. And usually the A1G, the highest frequency, is like the most obvious, and the EEGs are weaker, they're more difficult to excite, and so on. And we haven't really, I think we haven't pushed this enough, you know, like to get better signal than not. And maybe we could do a heterodyne or something. Then we could see like a lot of really weak ones. We haven't done it yet, but it's powerful. I think,
Yeah.
to look at the lattice motion.
Yeah, before I forget, he's slated to give a second talk tomorrow at 11 a.m., okay, in somewhat, please.
Follow on next question. What's the wavelength of the highest frequency photons?
The coherent phonon. It's like 5 terahertz or something frequency.
You want to compare it with the crystal?
They're like 150 wave numbers if you look in that, or wavelengths. It's far infrared. It's far infrared. Yeah. So we have
The coherence length is quite long compared to the crystal.
Yeah, the coherence time is long in these, and we don't understand yet. Some decay more rapidly than others. We don't quite know why yet, if it's defects or other things. And really high frequencies are sometimes hard to see. So because your Fourier, your pulse durations and things could be cutting off. So if you're really careful. So we saw the electronic was 20 femtosecond. That's much higher in energy.
Daniel, do you have a question about Dr. Exino? We are dealing with Dr. Exino every day these days. Yeah, so, Delena?
You mentioned about observing and transient adjustment things, like there are multiple things that you observe at different energies, right? So how can you characterize those things? Is there, like, for example, fluid dependent measurement that you can do and characterize?
Yep. So we have to vary the fluence and make sure that the process we're observing is just due to one photon, so that you can know that you haven't excited higher bands. So that would be a problem if you start getting into higher bands and you don't know what's going on with those upper bands and things. So we do power dependence. We have to raster scan the sample or change the repetition rate to make sure we're not changing the composition of the material or damaging it or things like this. And so there's a lot of checks to ensure that everything is okay. And then we have to think about all these main categories, like we create new carriers, new electrons in conduction bands. We have holes in valence bands. You could have holorons and other things, and what are all the quasi-particles that maybe we could see or not see. And then there can be like a band shift. Do just a red shift of, like, both bands can, get closer together because of adding carriers. You're weakening the bond. You can think of it like weakening the bond. So if you go to really high intensity, you can break almost every bond. And the material will reheal between the pulps. So you can see dramatic effects due to this. So we did that initially, and then we tried to go way down to lower intensity. So we just studied the basic properties of the material. So there's all these different things to consider. And there's broadening. So there's also line broadening things happening. We try to tease all that out.
I have two kind of more technical questions. You said you looked at molybdenum telluride and you had to look at 10 layers, but you had 50 nanometers listed, and that number seems a bit large for only 10 layers.
It might have been, well, I thought it was 10. It might have been 20, but it's, so we need about 10, like 20 nanometer to 50 nanometer to see a good absorption is what is limiting us. And for the particular element. So iron oxide could be much thinner than molybdenum telluride, and I don't know, what is the space?
It's about right. So because it's 2H, 2H has much longer, CH is lattice quantum.
2H would be
Good
two
check.
layers on top of each other.
There you go.
And the second question, you talked about the photon formation and how you can very visibly see it. Do they also see it in theory, or has there been like
So we did the theory.
Oh.
Yeah, and to show that this is how the spectrum would become Yeah, if it was a polaron.
Okay. Like
And so it is now, so it is a small polaron, and the Fe2O3 is a very bad conductor for, that's why everybody thought you should use like earth abundant elements and things, but like then you go to those like Fe2O3 and it's very bad for carrier transport. So, and the reason is the small polaron.
But have they looked at it from like first principles perspective?
I don't know that. Maybe I don't think so. But what we did is model it. You know,
Right.
yeah,
Just
and then did some theory.
thank you.
Yeah, 好的，正直。
There's a kind of analogy there. In chemistry, we have electron phonon and in cosmology or astronomy, there's like axion or axion photon.
Yeah.
And so since you mentioned this, I think the Attosecond
Where in astronomy, what would it be? Is it in X-ray, or where would you look for this axion?
maybe that's but anyway, for this analogy, do you think this
It depends on so it will depend on what are the forces involved, I guess. And so here, we have the Coulomb and normal things that we understand for atoms and molecules, and then we're looking for some Hamiltonian that does some coupling. So that part I know, but I don't know the astrophysical part exactly.
My comment is axion is axion, so it's the same thing.
Alright, so how do you choose which edge you look at?
Yeah. So the M edges are between about, say, 20 electron volts and maybe 90 electron volts for almost all the interesting metals and so on. And then we start to get into L edges. So silicon, we study the L edge at about 100 eV. And then if we can go, like we're going to build a new system to go to 650 electron volt, then we would be trying to address L edges. And that's much more standard for synchrotron and everything, and better understood. The M edges, when we started, there was almost no model for how to explain the spectra. So we had to kind of begin to invent that a little bit. But the L edges are far better understood. So we hope eventually we can be doing transition metals and more exotic things and up to 650 electron volt eventually. And if it's a carbon 1s or nitrogen 1s or oxygen, those are great because those are very well understood. And so we do that. We do 300 eV carbon. We did carbon nanotubes and things. I won't be talking about it, but and that was a great region to work in
Okay,
as well.
if you want to study the phonon coherence, what is the rule of thumb? What
Yeah. So I don't think we've unraveled yet. So I've been asking the people in my group, like, if the lattice changes by this much, then how many eV or milli eV change, and in the molecule, we've shown it's about 10 electron volts per angstrom if you work in angstroms.
So you are talking about a recoil.
Yeah, like the core level potential energy.
Okay.
And the steepness of the slope, the gradient of the slope is about 10 electron volts per 10 minus 8 centimeter or 1 angstrom. That's a lot. It's a really big change. But I haven't figured out what it is in a solid yet to think about it. That when we see a certain amount of excursion, so we see, the way you see those is by some excursion happening when the whole lattice is compressing and expanding. And I don't have a number yet, theoretically, to physically how to apply it.
So about the phonon coherence, are you trying to look for some material with a longer phonon coherence time, or so that you could
Yeah, so, you know, so we have just, in a way, started building a lot of data, I think, and finding some systems get like really great signal and some don't get any signal, and the some that have the Pyros distortion, they always give a good signal. So that's not a problem because they've been studied a lot previously by reflection and things like this, and we can't explain. So like molybdenum, like tellurium gives a huge, tellurium by itself gives a huge signal. It's kind of a screw-like lattice. It's really different, you know, and it gives a huge signal. And I don't know why. So I have not been able to put this together yet. Like, why is that one so big and so many others? Some others can be like almost zero. So we don't. You know, we've been going through like platinum telluride, gold telluride, like a whole lot of these, and trying to see why are some big and some are small, and I don't actually have an answer yet about it. You know. But I think when we figure it out, there'll be more to understand too.
Right. Smart people can implement such a phenomenon to devices. Make you rich. Right. Let's thank the speaker one more time.